everybody. Reporting to you again from the Glamour City, Hollywood.
So our goal is to be, let's say, as small as possible to perform the work of the design of the vehicle, and then support the production, which will be done by other companies which are already certified, which have already all the facilities to do this. And then also for the part of the sales, it's not Manta, but it will be Manta using or collaborating with the companies which have already their network. And this changes a lot the investment. It's really one order of magnitude difference when we think at the comparison between this model and the model of also having the manufacturing. Not to mention the model of having also the operation of the vehicle, because some business models that are out there include the design, the manufacturing, and the operation. And this is very, very capital intensive. That's clear. It's a totally different model. We are talking about the same sector of eVTOLs, but we are talking about also different models, very different models.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for our show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today I'm joined by Lucas Marchesini, CEO and CTO and co-founder of Manta Aircraft. Welcome to the show today.
Thank you, Scott. A pleasure being here.
Lucas, you have had a passion for aircrafts even as a child. I want to see if you could share a little bit more about that.
Well, yes, I know being passionate about aircraft is very heartfelt, and so when you have the passion about airplanes, you start, and then it's like a virus. And I started this when I was a kid, and then I carried on. I studied Aeronautical Engineering. I designed my first plane when I was at the university, and then I carried on from there.
Amazing. And what are the different types of flying vehicles that you have licenses for?
Well, I have been working mainly with airplanes, and airplanes means civil airplanes, defense airplanes, and then I'm a pilot as well, and I fly gliders and light planes, motor planes. But and then I have studied also about helicopters. I never worked in a helicopter company. I studied helicopters, the helicopter design at the university, together with the rest of the subjects. But now I have with Manta Aircraft, we have really the possibility to use also that knowledge. And obviously, we have specialists coming from the helicopter field.
So the reason I'm asking is your background is important because you're not only coming from the technical engineering background, but you're also a pilot, a user. You understand the user interface and some of the challenges, but also some of the opportunities, which brings us to Manta Aircraft. What is it, and how does a hybrid electric vertical takeoff and landing aircraft enable efficient long range, I think 300 to 1,000 kilometers at high speeds?
Yes, well, it's we use a special or dedicated propulsion system. We chose to go this way since the very beginning. We were contrarians at the beginning, because if you remember 3.5 years ago, everybody was going all battery. And then until last year as well, everybody was going all battery. We chose to do something different because our target was different. It was we were not targeting the urban air mobility, but the regional and interregional mobility. So in this way, we thought that there is a market there. I think there is a real demand for transportation for 200, 300, 500 kilometers. Because if you have to fly 1,000, 2,000, 3,000 or more kilometers, there are the airlines today. They are very efficient. The price is very reasonable. the whole system has been fine-tuned in decades and decades. If you have to travel short distances, there are other ways. There are in the cities. It's true that there is traffic, but you have the metro line, you have the underground, you have the buses, you have the last mile rental vehicles, and so on. But if you have to travel 200, 300 kilometers and you haven't got a high-speed train line, you have to go by car, and there is no other chance, or by bus. But anyway, so I think there is a clear market there where we can cut the travel time, by a good fraction, from maybe 3 hours to 1 hour, or 4 hours to 1.5 hours. So that was our goal since the beginning. And to do this, we need a different propulsion system. Batteries are not there, and they are not. They haven't got enough energy density to allow us to fly for more than 1 hour at 250, 300 kilometers per hour.
Yeah, you covered a lot of different areas, which I think is important from a nuance to really explore this, is that you're right. The last several years, we have seen kind of this whole entire focus on electrification of airplanes, which I suppose there is a niche market and certain markets where it's very small local travel. But the hybrid approach really allows for that extension. And you're talking about this gap where the market isn't quite efficient. You know, it's shorter than the greater than 1,000, 2,000 kilometers, but it's greater than that 200, 300. So it's kind of that sweet spot. Now, there are others that are also getting into the hybrid, but we still primarily, I think, it's either electric, all electric. Some are, you know, experimenting with hydrogen. But talk about the nuances of the hybrid approach and some of the complexities of having a dual approach, as well as some of the weight and some of the other impacts to that method.
Yes, it's true. I mean, you're right. Others are coming into hybrid because they have realized different things. Maybe a couple of things. One is that the business case of the urban air mobility is not as strong as it was thought to be, and so regional is more interesting. And to go regional, you need more energy on board, and you can have this energy only with liquid fuels today. And the other thing is that. Anyway, the logistics and all the system that is required to run a fleet of all electric airplanes is quite complex, and it's not so easy to put it in place. And what we have seen with the cars, it's an indication, but for airplanes, it's a bit more complex than cars. And so it's something that makes our life easier when we have a hybrid propulsion system. The hybrid propulsion system is for today. For sure, in 15 years, we will have a different landscape, but we have to bridge the gap between today and in 15 years. And we need something that can be operational in 1 year, 2 years, or 3 years quickly, not waiting for such a long time. Today, what are the challenges that have the batteries and the advantages of the hybrid propulsion system? The challenges of batteries are, we said already, it's a limited energy density. So for a certain weight of the battery, the amount of energy that we can have is limited compared to a liquid fuel, for example. But another challenge is the recharge, and recharge time is not as fast as to offer a stop and go for the vehicle, and it also comes with the batteries, the cost of replacing the batteries every certain number of cycles. And so if we think that today a battery that can be used today has a cost between $200 and $300 per kilo, and some of these aircraft, the full battery aircraft, have between 500 and 1 ton, 500 kilos, 1 ton of batteries, and they last. They can be used efficiently for maybe 600, 800 cycles. It means 800 flights. And if you fly 10 flights per day, it means 60, 80 days. So this means that you have to replace these batteries with this cost for these days, and you have to revert this obviously to charge this cost of the batteries on the passengers transported. So it's not so easy, let's say, to make the model work efficiently in terms of cost, but also if we think about the impact that we have on the environment with the batteries. We think about what it means to recycle or to have so many kilos of batteries that have to be disposed of or reused in some other way, but anyway, and they have to be manufactured. So this is not so not as green as we might see at the beginning, right? If we go deeper into the implications of this, what are the advantages in terms also of performance for the vehicle which has a hybrid propulsion system compared to battery system? It's like when we go with the car. If we go with the car, when we have a hybrid propulsion system, when we are at the traffic light, we can accelerate using part of the energy that is in the battery and using the electric motors. And we can, in this way, we can have a smaller internal combustion engine. In our case, we use the internal combustion engine only to produce electric power. So it's not used for propulsion. But the advantage is that the internal combustion engine, which is a small turbine, works always in the optimal regime. It's steady. Second advantage is that we do not need to size the turbine for the vertical takeoff and landing condition, which is very high demanding situation in terms of power required. Because in that condition, we use the power coming from the gas turbine and from the batteries. So we size the gas turbine for the condition of cruise, where the required power is lower. In this way, we have a smaller turbine, which is lighter, which is more compact. It's cheaper to buy and cheaper to operate and maintain. And we have the battery pack. And the battery pack obviously has also another advantage, because if we have to fly somewhere, overfly an area where we do not want to have the gas turbine running, we can shut off the gas turbine and fly only with the batteries. And we can fly for about 20 minutes just with the batteries. Or if we have a trouble with the gas turbine because we have a failure, then we can use the batteries to fly to the nearest airport. And in 20 minutes, 15, 20 minutes, we have a radius which is quite large. So we can find an appropriate spot to land without any trouble. And the same thing is, obviously, if we have troubles with the battery, we can carry on with the gas turbine. So there is a lot of flexibility. In terms of design, having these two power sources can allow us to balance them according to the mission, according to the weight of the aircraft that we want to create. So in some cases, we might want to have a stronger gas turbine and a smaller battery. In some other cases, we might want the opposite. So this is a balance that we have been studying in this time. We have developed our calculation tools to do this according to the missions, find the right balance between the gas turbine and the batteries. In this way, we can optimize the system for minimum consumption, for minimum weight, because the weight here is a key aspect, right? And the cost. So these are aspects that we have to bear in mind. Also, consider that at the end, when we have these vehicles flying around, the parameter that everybody will be looking at is the cost. So we have to design these aircraft that are capable of flying at a reasonable cost. And it means that they have an operating cost, which is limited, which is contained. So this is an aspect that we are looking at and are considering a lot during the design, because at the end of the day, after the initial enthusiasm because of the performance, then it comes the wallet. And there we need to really be effective.
So I appreciate you covering some of these aspects because they're really important. In regards to that balancing of gas combustion and the electric, is that when you talk about the different models, which we're going to get into in just a few minutes, depending on the configuration and the purpose and the usage, you're right, some may require greater power. others may require greater range. So tuning for that ability to configure on the use case is going to be critical. So I appreciate you talking about that. The other thing I think that is really important is that there is this barrier, which is there's initial CapEx, and it depends on who is purchasing it for what purpose. So if it's a fleet carrier, they're thinking not just the CapEx, but to your point, they're thinking about the OpEx. So for every flight, what is their cost structure? And can they actually have a consistent profit, recognizing that there's going to be maintenance and replacements every few years or so? So all of these have to be in place, and it's incredibly complex. Let's talk just real briefly about some of the infrastructure. The thing with eVTOL has been that certainly the ones that are actually trying to be classified under more of the air taxis, where you're looking to go from urban to suburban and so forth and be able to fly from anywhere. I think that's become clearly problematic, and there's a lot of issues around that. For your model, is it really more from a kind of a regional airport, existing infrastructure versus needing brand new infrastructure?
Yes, our goal was exactly this: start with a system, with an aircraft that can operate in the current environment without the need of adding something more, especially no need for recharge infrastructure, which is a topic, and no need for any special landing pad or takeoff pad. So we can fly with this aircraft. We can take off from a parking lot. We can take off from a small field. Can take off obviously from an airport, but the airport is already a limitation because there are some few airports. Okay, not in absolute terms. There are many airports, obviously, but they might not be very close to your location, and then if we are able to take off from any field or parking lot, then it's easier to set up a takeoff place where, for example, there is the station of the metro line. So you get there with the metro, you take off from there, and then you fly for 300 kilometers, and then you get to another city, close to another metro line, which takes you to the center, to the city center. In this way, we do not need an infrastructure to fly in the city, which is not easy to set up. And we are understanding also in terms of regulations, and then we might talk about regulations, which is an interesting topic here. And we do not need an investment to set up all this infrastructure in the city. So today we can take off from a small field, and also our vehicle is designed to perform a short takeoff. And in the short takeoff, it means 250, 270 meters, and we can increase a lot the maximum takeoff weight, which means that we can carry more payload or more fuel. So in this way, we can have it more flexible. Okay.
Yeah, I do want to table it for just a second, but I think the issue is when it comes to being able to fly or take off from any place, including parking lot or in front of your home for that matter, is going to be the regulation and compliance, which we'll parking lot for just a second. Let's talk about the different models. You have AN2, AN Plus, and AN Drone. Tell us a little bit about that, the configuration supporting some of those things.
As a first thing, I would say that we develop a platform, which means a platform in the same concept of the automotive platform. So it means all the technology that you need to have this platform flying. It means the systems, propulsion system, navigation system, human interface, and so on. The shape of the aircraft. So every shape has its own peculiarities, and we have invested in doing this test in the wind tunnel, CFD, computational fluid dynamics, many simulations for this. So we start from this platform, and then we derive different models. So all the models have the same, as much as possible, the same components. And the difference between them is that obviously the AN Drone is an automatic vehicle. It's an unmanned vehicle. And it has the same structure of the AN2, which is a twin-seater. And the same actually AN2 can fly both ways, manned or unmanned, or optionally manned. So you have somebody on board and you can optionally pilot the vehicle. It's meant to be used for missions where, beside the private sector, where everybody can buy it and obviously fly fly the airplane by himself, but it's meant to be used for mission for surveillance or organs transportation, which is a topic and a sector which is going to grow a lot, because it's these type of vehicles enlarge a lot the area where you can find the proper organ which is matching, which is offering a matching between the donor and the receiver. So if you have a vehicle which can transport them quickly on a wider range, then it's much easier to find the proper matching. Then we have the other missions, which are missions typical when you have an intervention, the need of a rapid intervention, or you need a technician that you have to take to a power station because there is an emergency. You can take him there, or you can take somebody to an oil platform, or there is the need of a doctor somewhere, and you can fire him there. The same, but obviously with more expanded payload capability as the N+. It's a 4 + 2 seats, so it means 4 seats plus baggage, or 4 seats plus other 2 seats and no baggage, or any combination in between. And all of them can also be used for transporting only goods. So the idea is to tap that market which needs services that today are performed mainly with helicopters. This type of aircraft is not designed to do hovering like the helicopter. The helicopter can stay in hovering as long as it likes. These type of aircraft, since they have a battery and they use the battery for the vertical flight, they have a limited amount of time, some minutes, that they can stay in vertical flight, which is enough for takeoff and landing vertically. But if we look at the missions that the helicopters perform, how many of these missions require the hovering? We have checked and we have seen that it's less than 15% of the missions. So it means that more than 85% of the missions of the helicopters require the capability to take off and land vertically, but do not require the capability to hover. And in these missions, we can fly this type of aircraft with an advantage, a direct advantage, immediate advantages of the lower cost. So this is the let's say the first market that we are tapping, and this is the market of the helicopters today, and it's an existing market. It's not a market that will come. It's not the eVTOL market. It's an existing market today where we can help and we can offer a machine which can be operated in parallel to the helicopters. It's not going to replace the helicopter; is hardly replaceable completely. But you can optimize the operations with helicopters using a machine which is cheaper. So this is the first topic. Obviously, when we talk about cost, obviously we have to go down the cost. And what is the projected cost, the projected operating cost of these machines? We are designing them to stay within the $300 per hour. So this is the operating cost that we are targeting. And if we think at a helicopter with this speed and range, it's about between 5 and 8-10 times more expensive.
So clearly, based on even just a rough estimate, is for those that are currently using helicopters for specific use cases, there's an opportunity to either augment or replace entirely, depending on if it's possible. But more importantly, I think there's going to be other uses where they probably can't afford a helicopter, but this could be something that could fit within their budget to allow for some of these missions that you're talking about. And I like the fact that you're talking about not just the consumer use cases, but first line workers and emergencies and other specialized use cases. I want to talk about some of the testing that's been done. So in 2020, there was a 1-to-3 scale prototype that was designed and used for optimization. And then you guys have also conducted large amplitude multi-purpose wind tunnel testing that you referenced before. And there's even digital twin that you guys talk about in terms of how you guys are replicating the propulsion system, the electric system, the flight control computer, as well as the fuel system as an example. Can you give us a sense in terms of where are you guys in terms of the product roadmap, as well as FAA testing and certification and eventually manufacturing?
Yes, for the design, we have our program is to complete the design within this year and start the manufacture on the first two one-to-one scale prototypes, to have them in the assembly phase by the end of next year. So the first one will be unmanned because it's simpler to fly an unmanned aircraft in terms of regulations dealing with the Civil Aviation Authority. And then the second one, which will be exactly the same like the first one, but manned, will come later because of the need for more checks and then different procedure with the Civil Aviation Authority. So we are talking about having these aircraft in the assembly phase at the end of next year in 2024. What we did was to go with the first 1/3 scale model. It flew only in 2020. We flew only in hovering mode, and it was meant to test the capability to stabilize the aircraft and control the aircraft with our algorithm in the computer that we had on board. It was just an electric aircraft, obviously. A plane, we don't put a gas turbine on it. It doesn't make much sense. But it was fundamental to understand how our control laws, the flight control laws, were working. And then the most delicate part, obviously, is the transition from vertical flight to horizontal flight and vice versa. And to do this, we started working on the simulator because it's obviously it's much safer. We don't risk to lose the model, and we can try different failures and different cases. So we started a lot working on the simulator, which is called also digital twin today, but it's basically a simulator which incorporates the different systems. And here we have the flight computer, aerodynamics and flight mechanics, and the propulsion system. These are the main systems that we have. And in the simulator, we have tried different ways of doing the transition, vertical takeoff, short takeoff, normal takeoff, failure of some of the motors, for the electric motors. So in this way, we can progress much more safely, and today it's a standard. It's a standard approach to go in the digital way. So we have our digital twin, which is called, it's basically a simulator, and the model of the whole propulsion system, which is running a dedicated software. And then we have the digital mock-up. So it's basically on the CAD. We have the drawings of the aircraft in the CAD, and where we try to check every part and how it fits, also in terms of manufacturing, assembling, and all this. So this is the status we have. We are targeting end of 2024 for the first two prototypes in the assembly, and start flying immediately with the unmanned aircraft, which will fly as a drone, as a fact.
So I want to talk about kind of the broader landscape that's out there. This year has been a challenging, to say the least, in terms of some of the macro environments. And we've seen broadly, certainly the autonomous side, whether it's trucks or consumer cars, have really struggled. And some of these have been publicly traded, others are private, and many have actually shut down. And then on the pure electrification, and I'm talking about more on the automotive side, even the ones that have publicly traded via SPAC or IPO have struggled. And we're seeing that even if they have single-digit billions in cash, it's really not enough. It's very capital intensive. And certainly when it comes to any kind of flying vehicles of any sort, though the enthusiasm is there, it's proving out that it's just capital intensive, it's challenging, and things may be getting pushed out. From your perspective, is that consistent with your view and what you're seeing in the market? And how do you overcome potential capital needs that you're going to have throughout the life cycle of the company?
Yes, I think this is interesting because it goes directly to the model, to the business model of the company. We have a business model where we position ourselves as designers of the vehicle. We do not intend to manufacture the vehicle. We have agreement with industrial partners, which are also in Manta, for them to manufacture the vehicle. This gives us the flexibility to manufacture the vehicle in different regions in the world without us being the ones investing in this. We are talking about an aircraft. So we are talking about a manufacturing procedure which has to be certified, which has to be done by a certified company. All this takes time, and it's very capital intensive. What we do, we focus on the design of the vehicle in the areas where we generate value. So we take as much as possible the technology that is existing and is off the shelf, and we focus ourselves on what is new and the parts which are new. We also have in Manta, as a shareholders, some companies which have specific technology. So they come and they participate to Manta and they bring this technology to Manta. This, let's say, makes our life easier because the core team does not need to develop that part. So our goal is to be, let's say, as small as possible to perform the work of the design of the vehicle, and then support the production, which will be done by other companies which are already certified, which have already all the facilities to do this. And then also for the part of the sales, it's not Manta, but it will be Manta using or collaborating with the companies which have already their network. And this changes a lot the investment. It's really one order of magnitude difference when we think at the comparison between this model and the model of also having the manufacturing. Not to mention the model of having also the operation of the vehicle, because some business models that are out there include the design, the manufacturing, and the operation. And this is very, very capital intensive. That's clear. It's a totally different model. We are talking about the same sector of eVTOLs, but we are talking about also different models, very different models. So this is a big difference, and obviously our capital needs are different, or a lot different from these big companies, other big companies, which include, you know, the other phases that I mentioned. It's true also that through the period that we are going through the periods that we are in, it's not easy to raise capital. It's even harder today. So I think a light capital approach might be more suitable to the current times. And also considering that there are resources worldwide for manufacturing that are underutilized today. There is some crisis. There are very good companies with decades and decades of experience, all the certifications that are needed. They are capable of manufacturing and assembling the vehicles. To us, it makes sense to make an agreement with them and exploit their knowledge and exploit their facilities to do this project.
Understood. Given that we have a finite time here, I want to circle back to the area of regulation, because, again, it's not so much a technical capability for vertical takeoff and landing anywhere, including rooftops and parking lots, and even smack in the middle of an urban city center. The issue is going to be new infrastructure as well as regulation. So there's talk about rooftop, but also dedicated landing spots for these types of aircrafts that needs to get built first, in addition to the regional airports. But the regulation that's going to then allow for it and flow, very much like the way we think about the way cars move in traffic, that type of a model within the air is going to have to exist. Where do you think FAA and FAA equivalent in Europe is with this regulation and allowance of such aircrafts to operate?
Well, we have seen a big development. FAA and the EASA have been working a lot on this. We have already some framework to base on. We are still missing parts, but there is already indication about the framework for the vehicles, framework for the landing infrastructure. Personally, I haven't seen all the regulations for the ancillary systems that are needed on a landing spot in case of emergency, in case of anything happens to the batteries, they catch fire. What do we do? How do we treat these batteries? We know that they are not easy to treat because they have lithium inside. Also, the approach paths, they have to be defined. So we see that EASA and FAA are progressing. FAA has stated recently that the basic regulations are the FAR 23, FAR 27, some parts of maybe FAR 29. So this is the reference for FAA. I think that there is the need to improve this, so to create dedicated regulations in some areas. EASA is moving more or less in parallel of the FAA. I think that from our side, these developers of these vehicles, there are still some gray areas in the regulations, not only for the vehicles but also for operation. And obviously, the regulations for operation impact the design of the vehicle. That's clear in a certain way. So we still need some time. And that's why our approach is to create a first model, which is the two-seater, which can be offered in the experimental category in the US. There are more than 27,000 aircraft in the US in the experimental category. So it's an aircraft which can operate in the experimental category without having a whole certification. It's an aircraft that can be used as a drone. So without all this, again, all that certification. And then as soon as the certification framework gets completed, then we move to the N+, which is the bigger one. So we have more time to get to certification, and we can go to market before reaching the certification point. Also, it's important to remember that certification in this field includes two categories, the basic and enhanced. There is a big difference between basic category and enhanced category. And if you want to do public transportation of people, of passengers, then you have to be in the enhanced category, which is more complicated, more expensive. If you are targeting other applications that are not those that require the enhanced category, you can stick to the basic category. And this is simpler. And this is what we are trying to do. Obviously, we are trying to target markets where the basic category is enough, beside the experimental category where we want to start first. No? So let's say that the development of the products originating from the platform that we develop is phased in such a way that we can go to market before having the full certification, and therefore also before that the whole framework is complete.
On the enhanced capability classification down the road, let's talk a little bit about user experience. At the time of this recording, there is a atmospheric river that's affecting pretty much most of the world at this point. And moreover, in the recent years, we've seen a significant increase in turbulence, wind, and velocity. And I wonder how something like this type of classification of enhanced vehicles would withstand that kind of turbulence, and what would be the experience for those that are actually in it?
I think this is a super important topic because we think that everybody will be flying these vehicles, but as a matter of fact, we know that many people are afraid of flight and are afraid of flight on liners. So imagine if they fly on something small, which is moving in the wind. So we have to guarantee that the ride experience is good. How can we do this? We can do it with the configuration of the aircraft, and we can do it with the electronics, obviously, with the system. So configuration-wise, this is also one of the reasons why we have this configuration. Is a winged solution. It's designed to be particularly stable, and the electronics is going to compensate also for updraft and downdraft effects on the ride experience. So this is important. I think it's important, like also having the design of the cabin. When you have the cabin and you have everything everything transparent and transparent plexiglass, it's fantastic to see it in the renderings, but I think that somebody being there might be very, very afraid of looking around and seeing the whole world below him, and so I think we still have to progress in this as a sector, thinking about the ride experience, and we have to try to guarantee that the effect of this turbulence is minimized. There are projects around that are quite efficient in reducing the effects of turbulence on the aircraft. And today, luckily, we have the electronic systems which can help a lot in achieving this goal. So a lot is let's say we put our hopes in the hands of the electronic systems to do the artificial stabilization in case of updraft, downdraft, and turbulence in general. But obviously, you need a good platform as a basic design, and this we hope we have. Since we have been thinking about exactly this when we design a platform which is basically an airplane, okay, with the capability to go vertical.
All right. So with that, I have been joined by Lucas Marchesini, CEO and CTO of Manta Aircraft. Thanks for joining today.
Thank you, Scott.
All right. If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.